This is a production of Cornell University.
So what are fumonisins? They are mycotoxins. They're mostly produced by Fusarium verticilioides. This is a fungal pathogen that causes Fusarium ear rot in corn. And this ear rot produces fumonisins. So we're interested in these because these mycotoxins are a health risk. So they're more common in tropical and warm temperate climates, such as the southern United States. And they're linked to a variety of health problems in humans, such as esophageal cancer, childhood stunting, and also they're a big issue in livestock, especially for pigs and horses. The FDA regulates this at a range, depending on the final product, from 2 to 4 parts per million. For today's talk, I'll be referencing the 2 parts per million limit mostly. And so here you can see an ear rot, and these white streaks on the kernels are signs of the fungal pathogen. Fumonisin B1 is the most common and toxic form of fumonisins. And so the paradigm that we're sort of working under today is the idea that Fusarium ear rot colonizes the kernels and causes the kernels it colonizes to be less dense. And if you decrease density, we think that then that will be linked to an increase in toxicity. So one way to mitigate fumonisins and their harmful effects is by sorting. There's all sorts of sorting methods. Some can be density-based, such as the gravity table here, which is often used for seed quality. Size-based sorting, such as screening out fines, which tend to be more toxic, and also spectral-based sorting methods, such as using near-infrared fluorescence to detect spectral characteristics of the toxin. And why do we want to sort? Well, a breeder might want a low-cost phenotyping alternative. A farmer might want to increase the value of their crop. And then in many parts of the world, such as sub-Saharan Africa, these are a large public health risk, and a post-harvest intervention can be beneficial there. And so in our lab, we've developed, with the help of a local inventor, John Fuchs, a density-based sorting device that we've termed the DropSort or DropStorm. And this device uses vacuum-based density sorting. So you can't see, but up here is a large fan that has a tube that connects to this hole here. And so it's providing suction through this plane. And then there are 2 bins at the bottom, left and right. And the advantages of this compared to maybe a gravity table is that it's much cheaper. It still has okay throughput, and we can adjust it here. So if you look at this cartoon of how it actually functions, you drop your unsorted maize, it drops 1 by 1 down. A less dense kernel will be more likely to fold towards the right side and land in your reject bin, where there's less dense kernels, which are putatively more toxic, whereas denser kernels are more likely to stay the left side and land in your accept bin. And so when assessing the efficiency and the effectiveness of your sorting, we think of concepts of specificity and sensitivity. Specificity being the rate of true negatives, how well you're doing at keeping your good kernels, and sensitivity, your rate of true positives, how well you're doing at rejecting the bad kernels. So to calibrate this device, we use 3D printed plastic maize. This work was started by Julie Wyshensky, a former master's student in our lab. And so on the top row, we have each color corresponding to a different density. We also look at different sizes, small, medium, and large, and different shapes, such as a sphere versus a kernel shape. And I won't show you all of these results, but it can, in fact, separate based on density, and shape and size also play an influence. And we also looked at how well resorting our accepted fraction. So sorting once and then sorting this fraction again, how that affects specificity and sensitivity. So now moving from the plastic to the real corn, we had Texas maize that was naturally infected by Fusarium And we had 1 kilogram samples that we resorted 3 times, as I described. And we measured bulk attributes like 100 kernel weight, bulk density or test weight, as well as total Fumonisins were measured by ELISA. And so we can see that our device did a good job at separating based on these bulk attributes. Here we have the different fractions, and 100 kernel weight was significantly reduced. We also see for bulk density, our rejected fraction was significantly lower. That's important. Laura Morales, a former graduate student, showed that there was a correlation between bulk density and Fumonisin. So not surprisingly, because of that, we were able to show that Fumonisins were significantly decreased by 80% in our accepted fraction compared to unsorted. And the rejected fraction had significantly higher Fumonisin levels. However, I should point out that if we're thinking of this as trying to meet some legal limit of 2 parts per million, our accepted fraction still had the majority of samples exceeding that. So I wanted to zoom in further to understand at the single kernel level what sort of traits were affected by this sorter, and also single kernel traits that could be related to Fumonisin. And so I took a subset of 72 accepted kernels and 72 rejected kernels from 1 sample and measured the mass, which is very simple just by placing it on a scale. However, to get the volume is a little more difficult as it's complicated to measure the volume of a small, irregular shaped object. So with the help of Ethan Stewart and Mike Orr's lab, we developed a small device that takes 36 pictures around the kernel, and then using code from a German group, uses volume carving to make a 3D reconstruction of the kernel that gives you a volume. Also interested in the visual appearance, and so I scored these kernels based on their symptoms, from 1 being asymptomatic, all the way up to 4 being highly symptomatic. Finally measured all of the Fumonisins in each single kernel by ELISA. So now I'll be showing you some histograms of each single kernel characteristic. And in single kernel mass, we have a significant decrease, where the dashed lines are the means of each. So our rejected fraction mean was significantly lower than accepted fraction in terms of mass. However, I want to point out that there's a lot of overlap between the two. Similar for volume, there was a significant decrease in the rejected fraction. So rejected fraction kernels tended to be smaller. However, again, there's a lot of overlap between the 2 distributions. However, when you just divide mass by volume to find density, we found no significant difference between the density of the kernels in each fraction, which is a little puzzling based on the theory of our sorter. However, I want to point out that the distributions here are much narrower than they were for mass and volume, making it more difficulty for a sorter to separate based on this characteristic. However, when we look at actual Fumonisin in our single kernel set, the transformed Fumonisin values were significantly lower in our accepted kernels, which is a good thing. And I also want to point out that the most toxic kernels that were orders of magnitude higher than this 2 parts per million limit were most concentrated in the rejected fraction. And here we can see we did have some false negatives sneaking in to our accepted fraction. So I now wanted to look at how each of these traits correlated to log transformed Fumonisin. And so if you direct your attention to the right-hand column, you can see that for each characteristic, there was significant but only slightly negative correlations with log transformed Fumonisin, indicating that single kernels with higher Fumonisin tended to be lighter, smaller, and less dense. And I finally wanted to look at, based on the single kernel data set, how well we were doing with the sorting based on specificity and sensitivity. So with our DropSort, we predict accepted was our accept bin. And we found true negatives of 94%, false negatives 6%, or those few that you saw just exceeding the limit in the histogram. However, when we look at our sensitivity, it's much lower, 13%. That means when we're sorting, we're getting a lot of those, we're misidentifying a lot of non-toxigenic kernels and having a lot of false positives. I wanted to compare this to how just your eyeballs would do. And so based on that visual scoring, classifying 1 to 2 visual score as accept and 3 to 4 visual score as reject, we had similar effectiveness comparing our machine to my eyes. So, however, the machine is much faster. So yeah, we had 95% specificity and 17% sensitivity. However, this does indicate that visual characteristics of the maize is important for understanding Fumonisin contamination. With all that being said, I'm working to integrate these tools with other sorting methods, such as visual near-infrared reflectance on the single kernel dataset as seen here. I'm also interested in using these tools on near-isogenic lines we have in our lab that contain fusarium ear rot resistance loci, and thinking of ways to use the DropSort to enrich samples with toxic kernels, and using various tools to measure single kernel attributes and see how those relate to fusarium resistance. So with all that being said, I'd like to thank everyone in the Nelson Lab, all of the wonderful collaborators who helped make this possible, and of course, funding. So welcome any questions.
This has been a production of Cornell University, on the web at cornell.edu.